So in this lecture, we are going to cover hypothesis, where do they come from, hypothesis testing, causality, types of data, variable and measurement, parameters, alpha and beta. We'll discuss in detail, mod, median, and mean. It should be mean. Frequency distribution, probability distribution, normal distribution, a very important part of today's lecture. Measure of dispersion, range, variance, standard deviation, covariance, and correlation. So this is all what we're going to cover in the lecture today. Let's get started. Before we do, let us have a quick revision on probability distribution and a little touch on the normal distribution. Probability distributions are a way to figure out how likely different outcomes are in a situation. For example, you have a large bag, and this large bag has got 40 red balls, 30 blue balls, and 30 green balls, a total of 100, right? Now, if you randomly pick one ball, the color you could get is not certain. It could be red, it could be blue, it could be green, right? But we can predict the likelihood of picking each color. Like for example, if I say, well, if I get one ball, what is the probability it's red? There are 40 red balls out of 100. So it means the probability of getting a red ball is 40%. Similarly, the probability of getting a blue ball is 30%. That is 30 out of 100. And of course, probability for green is 30 as well. So we are not exactly sure, but you can predict the likelihood of picking each color. So a common shape for data is the normal distribution. It looks like a bell curve. This bell-shaped curve, where most of the data clusters around the middle, the average, and the chances of finding data points decreases as you move away from the center, either towards the left or towards the right. Right? A simple example of this is heights of people. Most people are of average height. Very few are extremely tall, and very few are extremely short. So we will make use of normal distribution. So in short, probability distribution helps us understand and predict the chances of different outcomes in various scenarios. So that's what we're going to discuss tonight. And that's exactly what the slide says. Given a data set of scores with a common shape, we could accurately calculate the probability of any given score occurring using an idealized probability frequency distribution or probability distribution. So one of these common shapes we just discussed is the normal distribution. So here we go. This is the normal distribution curve, what you call the bell-shaped curve, and this is a fundamental idea in statistics that will help us understand how data behaves in real life. So let us take the same example. The heights of people in a city or in a college or a university, it is normally distributed. Means most of the observations, most of the heights will tend to cluster around the central value, the mean, with fewer observations appearing as they move further away from the center. Very tall, few. Very short, few. So you may say that heights that are much taller or shorter than average are less common, and that's where bulk of the people fall. Okay, let's say the average height in our example is, let's say, 170. Right? 170 centimeter is the average height. And the standard deviation is 10 centimeter. We will discuss standard deviation as we proceed. It's a way we calculate the dispersion in the data. We'll discuss in detail. So one standard deviation, let's say, of this data is 10 centimeter. Right? So what it means? It means that 68% of the data is within one standard deviation. Means 160, 170 plus 10, 180, and 170 less than 160. You know what it means? It means 68%, 34 plus 34%. 68% of the people's height would be between 160 centimeter and 180 centimeter. Expanding this range to two standard deviations, that is means that's 10 plus 10, 20, 170 plus 20, 190, and 170 minus 20, 150. So what it means? It means 95% of the data lies within two standard deviations. That is, 90% of the people fall in the height range of 150 centimeters to 190 centimeters. So these properties of the normal distribution are not just theoretical, they apply to many real-world scenarios beyond human height, like you can take blood pressures, readings, or many other measurements that tend to cluster around a central value or mean. In everyday life, understanding the normal distribution can help in making predictions. For example, if a teacher knows that test scores are normally distributed, they can predict how many students scored above or below a certain threshold, which can help in grading strategies or identifying needs for additional instruction. In healthcare, for example, knowing the normal distribution of blood pressure in population helps doctors determine when a patient reading are normal or when they might indicate health issues. So understanding normal distribution gives you a powerful tool for analyzing data and making informed decisions based on statistical likelihoods. So not just assumptions, but rather you're going to make some informed decisions. All right, let's see if we can generate something like this by an experiment. Let's see. What scores will we observe if we roll 2 dice? So now, the red dice show 1, 2, 3, 4, 5, 6, and the green shows 1, 2, 3, 4, 5, 6. Right? These are the possibilities for the 2 dice. So X here represents the sum of 2 dice. The red shows 1, green shows 1, the sum is 2. The red shows 2, green shows 1, 3. The red shows 3, green shows 1, 4. So it's very easy to construct this population of possibilities. And so on. The red shows 6, the green shows 6, the score is 12. So let us construct a distribution starting from 2, 3 up to 12. So 2, 3, 4, 5, 6, 7, 8, 9, 12, 11. So, and let's now write down the frequency of occurrence of 2. 2 occurs only once. 3 occurs twice. 4 occurs 1, 2, 3. 5 occurs 1, 2, 3, 4. And similarly, 11 occurs 2 times and 12 occurs only once. So this is our distribution. Now let us calculate probabilities of each occurring. So we have 6 times 6, 36 possible scores, possible sums. What is the probability of getting a score of 2? Only once out of 36. So 1 out of 36. What is the probability of getting an 8? 1, 2, 3, 4, 5. We already have it here. 5 out of 36. What is the probability of getting a score of 12? 1 out of 36. So if you complete this table, let me show you the next slide. 1 out of 36, 2, 3, 4, 5, and 4 out of 36, 2 by 36. And so this is the probability distribution showing you the probability of occurring the scores we see to the left of the screen. So if we take the score on the x-axis and probability on the y-axis, so we will get something like this, a normal distribution. Let me show you. So these are our scores. This is the probability, and you see. So you can see in this example, it is symmetrical. Highest for x here, and then declining on either side. Expected value of a random variable. Let us discuss what it is with the example we just described a little while ago. Definition of expected value effects. The expected value of a random variable, also known as its population mean, is the weighted average of its possible values. The weights being probabilities attached to the values. Let me explain this, what it says here. So expected value, how is it calculated? Expected value is calculated by multiplying each possible outcome with its probability. 2 times 1 over 36 plus 3 times 2 by 36, 4 times 3 by 36, and we keep on doing it. And if we add all the results, if we do, it will give us 252 divided by 36, which is 7. So what we have done, look at the formula. This is the possible outcome times its probability. Possible outcome times probability. So x1 2, p1 1 over 36 plus x2 3 and p2 2 by 36. So it's sum of all these outcomes times their probability will give you a total of 252 by 36, which is 7. And what does it mean? It means the expected value or the mean of rolling 2 dice is 7. This is the average sum you would expect to roll if you roll 2 dice a large number of times. And if you see the graph, let me show you. And the graph confirms that that shows you 7 as the highest value, most likely outcome. And further, you can observe that the distribution is symmetrical around 7. See, with probabilities decreasing as you move away from the central value. So this is a practical demonstration of how expected values summarizes the center of a probability distribution. So we got just this one number, single figure, that represents the average outcome over many repetitions of the same random event. So let us now summarize the description of the data. The mean of 7 lies at the center of the distribution, and it has the highest probability of being observed, that is 6 out of 36, or 1/6, or in percentage terms 16.67 rounded to 2 decimal place. Let's see. Yes, this is it. Mean is 7. It lies at the center of the distribution. It has the highest probability, 6 over 36. If simplified, turns into 1 over 6, and if expressed in percentages is 16.67. Perfect. The lowest score to the minimum lies in the lower tail of the distribution below the mean. Okay, true, true, true. The low score 2, that's the minimum, lies in the lower tail of the distribution and clearly below the mean. Okay, the highest score 12, the maximum value, lies in the upper tail of the distribution. Let's see. This is true as well. The highest score 12 is the maximum value and it lies in the upper tail of the distribution. This is the lowest tail and this one is the upper tail. And this is the most repetitive value with the highest probability. The range is 10. What is range? The difference between the minimum and maximum values. Okay, let's see. Maximum minus minimum, 10. True. 2 and 12, these two scores have the lowest probability of being observed, 1 over 36. Okay, let's see. Absolutely right. 2 and 12, they have the lowest probability of being observed, and this is verified through this example. Okay, next important topics for today, variance and standard deviation. One of the things we are interested in is how much variance there is in a data set. Variance and standard deviations, these two are statistical terms used to describe how spread out or how scattered data points are in a data set. So let me explain these concepts using a simple example. Variance measures how much the numbers in a set differ from the average of the data set elements. If all numbers are the same, then variance is 0 because there is no difference from the average. High variance means the numbers are very spread out from the average, and low variance means that they are close packed around the average. Let's see, we have an example here. Suppose we have data for 2 car dealers showing the number of cars sold in the first 6 months of the year. Dealer 1 sold 6 cars in first month, 14, 30, 22, 30, 23 and 16 in first 6 months respectively. Dealer 2 sold these cars in each of the 6 months. So which data set or which dealer has the greatest variance? And this is the formula we are going to use to calculate the variances for both of these data sets or these dealers, dealer 1 and dealer 2. So this is it for dealer 1, 6, 14, 30, 22, 23 and 16 numbers of cars sold in 6 months. 6, 14, 30, 22, 23 and 16. So sum of the cars sold is 111 and the number of months 6. So you take 111 upon 6. This gives you the average, the mean, and it is 18.5 right here. Right, so this is X. This column here is for the element in data less mean. 6 minus mean, 18.5 minus 12.5. 14 minus mean, 14 minus 18.5, negative 4.5. And you do the same for others. Then these deviations squared as per the formula. So negative 12.5 squared, negative 4.5 squared, this, and then finally negative 2.5 squared. And adding all these gives you summation x minus x bar squared, which is 347.5. And you divide it with n minus 1. N represents the months, 6 months. 6 minus 1, 5. So this gives you 69.5. This is called the variance. And it measures how much the numbers in a set differ from the average or the mean of the set. Let us calculate this for dealer 2 also. But before we do this, there is another concept called standard deviation, which is nothing special. It's just the square root of the variance. Standard deviation is the square root of the variance. So simply take the square root of the answer we got previously, and this is what you call the standard deviation. Then what's the difference between these two? Variance measures the average of the square differences from the mean, while the standard deviation is the square root of the variance. Alright, now let us apply the same idea and calculate the variance and standard deviation for the second car dealership. And this is the data set we have. 7, 3, 6, 2, 8 and 10. Let us put in the table. 7 plus 3 plus 6 plus 2 plus 8 plus 10 gives us 36. And then we calculate mean. That is 36 divided by the number of months. 6. Mean is 6. Next we calculate deviation from mean. That is 7 minus mean, 3 minus mean, 6 minus mean, 2 minus mean, 8 minus mean, and 10 minus mean. So we got deviations. Deviation squared, 1 square 1, minus 3 squared 9, 0, 16, 4 and 16. Sum of the square deviations, 46. So variance is 46. Less n minus 1, that is 6 minus 1, 5. So 46 upon 5, we get 9.2. And standard deviation would be the square root of the variance. And if you calculate it, it's going to be 3.03. So this is it. This is the variance of dealer 1, dealer 2, standard deviation of dealer 1 and dealer 2. So clearly, this tells us that this data has more spread. It is widely scattered, distributed, but this one is tightly knit because it has a lower variance or standard deviation. Okay, so please, an important point that you should always remember, summation x minus x bar whole square upon n minus 1. This is called sample variance. And if you replace it with n only, this is called population variance. Now, what is the difference between these? Population variance divides the sum of square differences that you see on the numerator, right, by the total number of data points, n. Whereas, when you talk about sample variance divides the same numerator with n minus 1 data points, right? Data points minus 1 to provide a better estimate from a subset of data. Like, let's say this is your whole population representing n. A sample drawn from this population has to be smaller than the population, right? So it has to be less than the population, so that's n minus 1. So this n minus 1 factor provide a better estimate from a subset of the whole population. And of course, when you take the square root, it becomes standard deviation. Remember, just to emphasize again, this is the variance for the population variance, and divided by n minus 1 will give you the sample variance. Now we're going to do an interesting example. We are going to compare two variables and see how they are connected to each other. What is the kind of relationship or specifically correlation between them. So we have two variables, books read, exam marks. A student 1, he read 3 books, he got 56%. Student 2, he read 1 book and he got 57%. And the one who didn't study any book, he got 45%. And the one who read the most, 5th student read the most number of books, he got 65%. So clearly we can see that there is a positive correlation. If you study more books in general, you are going to get higher score. Apparently that is what we can see from this table given. But let's say if we want to prove this statistically, we want to get some computational evidence that yes, there is a positive correlation, that they move in the same direction. So how is it done? We do it using covariance. Let me show you the formula. So this is what you're going to use as a formula to calculate covariance between x and y. X is the number of books, y is the percentage score. So the formula is simply, as you can see, x minus x bar into y minus y bar and sum and divided by the total data elements in the data set. And this will give you the covariance. Let us just calculate and then I will explain how it works. So this is what we're going to do to calculate the covariance of x and y, to see how x and y vary together. First we calculate the mean of x and y, that is basically the x bar and y bar. So what we do, we take the number of books that have been read by these 5 students. So total number of books is 10 upon 10 upon 5. There are 5 students. So it's going to be, the mean is 2. Okay. Then the mean of y, the marks obtained. So you add all the marks, and there are 5 students. So adding these, dividing with 5 gives you 54. So mean of x and y, which is basically x bar, y bar, we got. Next step is to calculate x minus x bar. So 3 minus 2 gives you 1. 1 minus 2 minus 1. 0 minus 2 minus 2. 2 minus 2 0 and 4 minus 2 2. So this is x minus x bar. This element is completed. Next we have y minus y bar. 56 minus 54.8, 1.2. 57 minus 54.8, 2.2. 45 minus 54.8, negative 9.8, and then these two. So we've got y minus y bar as well. Now we need to multiply them as per the formula. So multiplying these, this into this, 2.2 into minus 1, and then adding all the results give us summation x minus x bar into y minus y bar. This is 39. So you need to plug this as the numerator, 39, and you divide it with the 5 to get the population covariance. But if you want to get the sample covariance, that's 39 upon n minus 1, 5 minus 1, 4. So that's it, 39 upon 4. This 9.75 is the covariance of the sample, or the sample covariance. So this covariance 9.75 doesn't reveal much whether there is a positive connection between x and y or negative or no connection. So for this we have a more refined way to find out how x and y are connected with each other. How can we define the relationship between x and y? Let's see. This is how we are going to calculate correlation, how two variables are connected, using covariance to calculate the correlation between two variables, x and y. X, number of books read, and the score obtained in exam. So first calculate covariance of x and y, which we already have. Then you need to, this is the numerator of the formula, this is the coefficient of correlation, and then calculate the product of standard deviation of x and standard deviation of y. We know how to calculate the standard deviation of a single variable. And then once you calculate the standard deviation of x and y, you use this formula and then calculate the correlation coefficient. Let me show you. So inputting covariance and dividing with the standard deviation of x and y, which you can calculate. We learned how to calculate standard deviation previously. And then divide the covariance with the denominator. What you get is 0.83. This is called Pearson correlation coefficient. The value of this coefficient is range bound. It cannot be less than -1. It cannot be more than +1. So what do we understand from this? Like for example, in our example, we got 0.83. What does it signify? What does it mean? It means that R is closer to +1, means x and y have a very strong positive correlation. Let's say in the previous example, had we got R, sometimes called rho xy, our coefficient of correlation, or rho xy, whatever the name you want, Pearson coefficient correlation. Let's say had it been +1, it is called perfect positive correlation. That means x and y are perfectly correlated with each other. When x increases, the number of books read, y increases. When x falls, y falls, and they fall and increase exactly in line with the same proportion. This is called the perfect positive correlation, right? But in our example, it's 0.83, positive 0.83, which still means it's not perfectly positive, but it is very strong positive. Similarly, had we got R is equal to 0, that means, or rho is equal to 0, that means x and y are not correlated. And if R was -1, it means they are perfectly negative correlated. Let me show you a more relevant example. So this correlation coefficient or coefficient of correlation shows you the strength of the linear relationship between two variables called coefficient of correlation. The value for R ranges from 1, perfectly positively correlated or perfect direct relationship, to -1, that is perfect inverse relationship. If two variables have a perfect positive correlationship, R would be +1. If they are negatively correlated, they will have a coefficient of correlation -1. But if anything falls between 0 to +1, like in this case +0.7, strong direct relationship. And if you get something like this, x and y, clearly there is no pattern trend, then the variables x and y, they have no correlation. Alright, so this is the interpretation right here. If it is negative, there is an inverse relationship between x and y, inverse correlation. If it's positive, there is a positive correlation between x and y, and if it's 0, there is no correlation. And if you ignore the sign, you just take the absolute value, whether it is negative 0.79 or whatever, absolute means it turns positive. So if you ignore the sign, take the absolute value means if you ignore the sign, negative, positive, just take the number. The closer it is to 1, there is a strong correlation, and closer it is to 0, there is less strong relationship. If it is exactly 0, that means there is no correlation. So we calculated coefficient of correlation to be 0.83. You may call it rho xy. So we need to test whether rho is statistically different from 0. For this we will conduct a hypothesis testing, but not now. We will learn it as we proceed in our lectures as we go along. So what we calculated here are as 0.83. What we want to assess now, is it statistically significant? Can we just use this generalization and apply to all the student population in the US, for example, that studying more books means you get a higher score in your exam? We just want to analyze this statistically. So we are going to make use of t-value. T-value will help us determine if the results from the sample which we are going to use are likely to reflect true population parameter. Means if can we conclude that studying more books you get a higher score? Is it true for the whole population, or maybe they just occurred by chance? So what we got for now, we got a correlation coefficient 0.83. The correlation coefficient is not normally distributed. It follows a t distribution. Okay, what it is, we learned this is the normal distribution, right? But a t distribution is flatter. It's like a normal distribution, but a flatter one. And as n increases, the sample size, the number of data set elements, then the t distribution converges to normal distribution. It keeps on going up, and then it becomes a normal distribution. So we are going to test the value of rho. Is it statistically significant? So what we are going to do, we are going to make use of t-test. We are going to make use of a very interesting concept, t-test. What is t-test? T-test is used to determine if there is a significant difference between two sets of data, set A and set B, or in our example, we are just considering one situation, a linear relationship between x and y. X, number of books read, and y, the score. So t-test is used to determine if there is a significant difference between two sets or a significant linear relationship between two variables, and that's our example. So the formula we're going to use is this one. This is called t-value. T-value is a statistic calculated from sample data. We were discussing a little while ago, and it measures the size of the difference relative to the variation in the sample data. How vary does it do? How strong the relationship is? How significant the linear relationship is between two variables? So when you use this formula, you input the values. What values you're going to input? Here we go. N was our sample size, 5. 5 minus 2, 3. Alright. Coefficient of correlation, right here, 0.83 in the previous slide. Yes, 0.83. So what we have 5 minus 2 square root 3 multiplied by the coefficient of correlation, that is 0.83, upon 1 minus r squared, 0.83 squared. So when you simplify it, simple maths, you get 2.6. Okay, now what does this tell us? So this value itself doesn't tell us anything. Let us take some help from the formula itself. This n minus 2 here, this is called degree of freedom. So for correlation test, the degree of freedom, also called DF, you will find this term DF in the tables we'll shortly see. Degree of freedom are typically calculated as n minus 2, where n is the number of data pairs, right? Next point, we need to next choose a significance level. Researchers need to choose a significance level like 5% or 1% or 10%. So these percentages, they represent the risk level of concluding that a correlation exists when it really doesn't. Like for example, if we test T at 5% level of significance, it means there is a 5% risk of drawing a conclusion that there is a correlation. In fact, there is no correlation. If we take the significance level 10%, that means this is the risk we are taking in assuming that the correlation exists, but it may not be so. We are going to discuss in detail. This is called type 1 error. So we will discuss all these in sufficient detail. So you are going to test your score 2.6, the T score, the T value. You then compare the calculated T value to the critical value in a T distribution table. Let me show you how. The first thing you need to do is to decide whether to use a one-tail test or a two-tail test. One-tail test normally looks for an effect in only one direction. We are going to discuss hypothesis testing later in detail in our later slide. Just to understand the idea right now, I'm just going to push this point of the topic. So in one-tail test, we are looking for an effect in only one direction. Why? Because in here we believe that X and Y are correlated in one direction. If you study more books, you get higher score. If you study less number of books, you get less score. So we are just trying to look for in a single direction. So we are going to use it one-tail test only. Because we can't think of a reason why the correlation would be negative. We could choose a one-tail test just to look at the positive part of the distribution to see whether there is a positive correlation between X and Y. So using a one-tail test, the theoretical value of T using 95% confidence interval with n minus 2 degree of freedom is 2.35. What does it mean? It means that if your calculated T value, which we just calculated, is greater than 2.35, you can be 95% confident that there is a positive correlation between your variables. And this result is statistically significant. And it further shows that the likelihood of obtaining such a correlation by just chance is very low, that is less than 5%. Let me show you how it's done. This is your degree of freedom 3, one-tail test. Critical value is 2.35, and you are right here. Why here? Because our T score is 2.6, which is greater than the critical value. So we can say that we are 95% sure that the correlation coefficient is significantly greater than 0. So we expect a positive correlation between books reading and the exam marks. That's the conclusion. So the question now we need to answer, why we did not use two-tail test. Why? We already answered this question briefly, but let me explain why. A two-tail test tests the hypothesis that is significantly different from 0, but it could be positive or significant or negative or significant. What does it mean? It means that a two-tail test is used when we are interested in determining whether there is a significant effect in either of the two possible directions. It is possible that some students study more book, they may get more score, or they get less. So it means the two-tail test doesn't limit the investigation to just in one direction. it studies in both directions. It could increase or just decrease. Instead, it checks both. So this is the difference between one-tail and two-tail test. I've just given you an overview about hypothesis testing just to push this topic. We are going to discuss in detail how we test hypotheses and how critical values and how the tables, everything is coming in detail in the subsequent lectures. But just for this lecture, we are going to keep it till here.